Hi, this is Charlie. Welcome to our next lecture for Introduction to Computing. Unfortunately, I have to shoot this lecture a little early because I have an uncle who is in the hospital and I need to go see him tomorrow. So I'm shooting the lecture tonight. So let me share my screen and we can get started. Okay, so here we are. We're on Module 6 operating systems, which I find much more interesting than some of the other contents. So here's a great link. Watch a crash course in operating systems. Okay, that's good. Brookshire, chapter 3. Of course, there's a quiz, there's the assignment, and the discussion. Okay, so let's get to the lecture. Okay, so here we are, chapter 3, operating systems. And we're going to cover the history, operating system architecture, coordinating the machine's activities, handling competition among processes, which is very important, right? And operating systems because you usually multi-threaded operating systems, you have multiple processes running and the security, of course, very, very important. We'll cover that briefly. Here are some examples of operating systems. I think we recognize these: Windows, Unix, Mac, Solaris, Linux, right? So nothing, this should be new here. So when you think operating systems, maybe you won't think of smartphones, but they have operating systems. So Apple iOS, Windows Phone, Blackberries. If anybody has a Blackberry, that would amaze me because I don't think that's too popular. Nokia's and Google Android. Functions of an operating systems to oversee the operation of the computer, right? Store and retrieve files, right? So we're all used to, I think, using, for example, Windows. I think a lot of us use Windows, and of course, Windows oversees the operation of the computer Windows, and of course, you're always storing and retrieving files. Provide the user interface to request execution of programs. Again, the Windows, the graphical user interface. Now, you may be a Linux guy, and maybe you don't like graphical user interfaces and you like the command line. Okay. Coordinating the execution of programs, right? So you want to execute stuff. You want to run programs, run applications, right? So it has to coordinate the execution of programs. Here's a history of operating systems. Each program is called a job. Early computers required significant setup time, right? And each job required its own setup, right? Operating systems again as systems for simplifying setup and transition between jobs. Now, I remember even the days of punch cards. Very interesting. So anyway, let's move on. History of operating systems, batch processing, right? You'll have a job queue, interactive processing, right? Process information in real time, time sharing. You have one machine but many users, like a mainframe computer, right? So there's the time share. Multitasking, one user, many tasks, right? So it's nice that if you're on one computer, you might want to open up a Word document. You might want to go on the internet. You might have Excel and so forth. One user, many tasks. Multiprocessor machines, load balancing, right? So they load balance all these processes. Embedded systems for specific devices like Internet of Things devices, right? They could have their own embedded systems. Here's an example of batch processing. So here jobs. So here's the user domain. So you have jobs that contain the program, data, and directions. You submit the job, the machine domain has a job queue, and then the job is executed, and then you get the results. Okay, nothing uh, rocket science here. So interactive processing. So here's an example of programs, data, directions where there's interaction between the program execution, right, and the machine domain. So maybe you're running a program. If you think of it this way, it says, okay, enter your user ID, enter your password, you do that, and it comes back, there's your logon screen, and then you go to the inventory link, and then it brings you to inventory, then you have to put the inventory item in, and so forth. So there's an interaction between the program. Operating system architecture. There's application software, performs specific tasks for users, productivity games, software development, and so forth. So that's the application. And then there's system software, provides the infrastructure for the application software. It allows you to execute the applications. It manages the memory. It manages the processes. It manages I/O, right? Consists of operating system and utility software. That's the system software. Here goes an example of software classification, right? So we're here dividing the software into application software and system software. So an application could be something like Microsoft Excel, Microsoft Word, and so forth. That's an application. And the system software could be a utility, right? So uh, maybe it's the utility allows you to look at what's the processes that are running, right? That could be something like this on Windows. Task Manager, right? There's an application, and that's showing the processes, the amount of CPU and memory, disk, and so forth. So there's an example of a utility, and of course, then the system consists of the operating system, which could be the user interface, right? That could be Windows, and then there's a kernel which manages at a lower level the processes, the memory, and so forth. Operating system uh, components, the user interface communicates with the users. You could have a text-based user interface, right? So uh, maybe DOS, right? You get to a DOS prompt and you do dir, for example. That's a text in it. And then there's the graphical user interface, which you were more used to uh, when you, for example, use Windows. And I think most of us would rather use a GUI than a shell. Uh, the kernel performs basic required functions, right? It does the file manager, manages file, device driver, memory manager, scheduler, and dispatcher, scheduling processes and jobs, and dispatching them, taking them. The user, okay, figure 3.4. The user interacts as an intermediary between users and the operating system kernel. So here's this picture. All this is showing users interfacing with the user interface, like for example, Windows. And depending what you're trying to do, it'll go to the interface with the low-level kernel, the actual guts of the operating system. Okay. Here's File Manager. So example File Manager. I think we all know this, right? For example, here, Windows File Manager. It's interesting here. Uh, there's an example. I can see downloaded files. You have documents. You cruise into different subdirectories, and you can find the files you want and so forth. So the directory or folder, user created bundle of files and other directories, right? The directory path is sequence of directories within the directories, right? It's the path where these files are located. Memory Manager allocates space in main memory. Okay, so you have to manage, the operating system is responsible for managing the memory. May create the illusion that the machine has more memory than it actually does. It uses virtual memory. So if it's a lot that's being requested to put in memory, it'll use virtual memory. That means the virtual memory, I would think of that as using disk. It's using your hard drive, right? By playing a shell game in which blocks of data, pages are shifted back and forth between main memory and mass storage. Getting it started, bootstrapping, it's called. A bootloader performs in ROM, read-only memory, run by the CPU when the power is turned on. It's a spot that starts the operating system. It transfers the operating system from mass storage to main memory, okay? Executes a jump to the operating system. That's at the bootloader, loading when you load the laptop. The booting process, here's an example. So in main memory, you have a spot here, the bootloader, and you have volatile memory. So in step one, the machine starts by executing the bootloader program already in memory. Operating system is stored in mass storage, okay? So, and then step two, the bootloader program uh, directs the transfer of the operating system into main memory, as you can see here. Here's an example of the operating system coming from disk storage onto the operating system, and then transfers control to it, right? So there's an example of the bootloader. Coordinate the machine's activities. An operating system coordinates the execution of application software, utility software, and units within the operating system itself. Okay, let's go over the concept of a process. I think we should have a general idea of a process. It's the activity of executing a program. Okay, so status, the process state, the current status activity, right? So we all know that there's a program counter. We know that from the work that we've performed. There are general purpose registers, and there's a related portion of main memory. Process administration, right? So we have be able to administer processes, the scheduler. It adds new processes to the process table and removes completed processes from the process table. So, and when you talk about a schedule, the scheduler could be an application to schedule what you want to run and execute. But we're also talking about a schedule inside the kernel. Okay. Now, the dispatcher controls the allocation of time slots to the processes in the process table. Okay, so the end of a time slot is signaled by an interrupt. So that's dispatcher, right? Controls the time slices to the processes. Okay, here's an example of multi-program between process A and process B. So let me go over that. So here's advancing time. There's a process switch here. So there's no process B executes for a certain amount of time. Then there's a process switch and process A executes over a time slice. Then there's a process switch and B and A, and they alternate. So this is a way of scheduling uh, for processes to execute, so each gets a fair amount of time to process, right? So the process B, for example, doesn't, when it starts process B, it just doesn't run forever, and then process A can't get any processing done. Okay. Handling competition among processes. How do we handle that competition? So there's semaphores. It's like a control flag, right? When you turn the semaphore on, no other process can access it. Then when you turn the semaphore off, they can. A critical region, a group of instructions that can be executed by only process at a time, right? So there's a critical region. Okay. Mutual exclusion, requirement that only one process at a time be allowed to execute a critical region. So there's semaphores, critical regions, and mutual exclusion. And this is needed, right? For handling competition among processes. There's a deadlock. A deadlock can happen. Processes will block each other from continuing because each is waiting for resources that allocated to another. So each process they're waiting. They're deadlocked. They're banging into each other. Conditions required for deadlock: competition for non-shareable resources. Resources requested on a partial basis. An allocated resource can be forcibly retrieved. Deadlock result. Here's an example of a deadlock, and we're showing a train, right? So here's an example. So each the tree, but both each train is blocking each other, right? So there's a deadlock. Now, security. Okay, this is my area. Attacks from outside, right? So there are attacks from outside, external, and maybe the problem could be an insecure password. Maybe you allow access to a Windows machine to run RDP, remote desktop protocol, and that's public facing, and you have a weak password and they hack into you, right? So sniffing software. So they sniff the network to see if they can glean any information that could be used. Countermeasures, auditing software, right? Software that audits it. There's a lot of countermeasures. And this is not a course on security, right? And this is a high level course. So security in itself would be a course in itself, operating system security. So auditing software. Attacks from within a process. There are attacks from within, internal attacks. Process that gains access to memory outside its designated area, right? And there could be countermeasures, control process activities via privilege levels and privileged instructions, right? So it's trying to gain access to memory. This is common with malware. And so that's all we had on operating systems. I just want to make sure that's the case. Uh, so that was pretty quick. Let's take a look at the assignment. Let's see here. So if I recall, I remember last time this assignment's interesting. Okay. Understand the basics of computer architecture, identify, blah, blah, blah. Okay. List four activities of a typical operating system. We discussed them in the lecture, right? So memory management, process management, user interface, things like that, right? So summarize the distinction between batch processing and interactive processing. I think you'll understand that. Suppose three items R, S, and T are placed in a queue in that order. Okay, so you have to understand a queue, right? So there's a queue. The processes are placed in a queue, right? So you have to understand how a queue operates. The one item is removed from the queue before a fourth item. Okay, so there's a question about a queue. Think we should understand that. Suppose a computer contained five main memory and the operating system needed to create virtual memory twice that size using two pages. How many pages would be required? There's a perfect um, question to put in ChatGPT. Okay, be honest with you. A process to be I/O, but this is interesting. A process is said to be I/O bound if it requires a lot of I/O operations. So, whereas a process that consists of mostly computations within the CPU memory is said to be compute bound. So you have an I/O bound and a compute bound. If both compute bound process and I/O are waiting for a time slice, which should you give priority and why? So that's a very interesting question. Identify three ways in which a process could challenge the security of a computer, right? So the process may be privilege escalation, accessing memory, and so forth. Okay. So, okay, this is an interesting question. Suppose a password consists of a string of 9 characters from the alphabet, 26 characters. If each possible password could be tested in milliseconds, how long would it take to test all possible passwords? So you're looking for all the different combinations from the 26 passwords, and then each one's a millisecond, right? So you could calculate that. Like I said, in the course, the first two assignments were the most difficult. I think now we're getting into some interesting stuff. Quite honestly, I don't think it's as difficult as like trying to do the machine cycle and take care, be careful of memory and do machine language programming. This is at a much higher level. And that's why you, for example, use an operating system because you don't want to be doing it manages the computer. You don't want to have to manage the memory yourself, right? You want it to manage the memory for you or manage the processes. So that's the homework. So this is a shorter lecture tonight. I think that's good. Um, so give it your best shot. I may follow up with another lecture, maybe next week on operating systems, something interesting on operating systems. We shall see. I may not. If you have any questions, further questions about operating systems, please let me know. I'd be more and glad to help answer your questions. But like I said, I think we should all have a good feel for operating systems. And usually in college courses and undergraduate and maybe even masters. Usually there's multiple operating system courses like operating system one, operating system two, maybe even a Linux kernel course where you program the Linux kernel. And so this course is a very high level introductory course and we could never go into that kind of stuff in great detail. But if you're interested in operating systems, then maybe search. I think University of Arizona probably has additional courses on operating systems. Search for them. I find this topic interesting, but of course, I find networking systems even more interesting. I think that's the next course. Let's see the next content. So what do we have left here? We're getting pretty far into the semester. So we operating systems. Okay, we have only networking and the internet, which I find very fascinating. And then we have the final. Okay, so we're almost there to the end. Okay, so I just want to again I'm sorry that I had to shoot this lecture tonight on a Sunday night, but my uncle got very sick and he's in the hospital, and I need to go see him tomorrow night and speak to his doctors because I'm his caretaker. So I have to be there. Okay, so good luck on the homework. I'm very happy with the class. I think everyone's doing great, and hope you have fun with these questions. Again, use LLMs to help you. If if you're not sure. But when you use the LLMs, ask it also, remember, always ask it to please not only give the answer, but please explain the answer. Why, you want to learn from it. You just don't want the answer, you want to learn from it, okay? And then include your prompts in your answers. Okay. Okay. So I just want to wish everybody have a great night. Good luck, and we'll speak in 2 weeks. Take care. Bye.